In this video, I want to take a look at graphs of functions of three variables. Now, with graphs of functions of one variable, we had one axis for the input variable and one axis for the output variable. For functions of two variables, we had two axes for the input variable. So we had a plane worth of input and we had one axis for the output variable. So the graph was in 3D. Now I've got three input variables, and so I've got a whole space worth of input, and then I need another direction for the output. And so the graph of a function of three variables is going to be out in the fourth dimension, which makes it a little challenging to see. However, we can get some insight as to what's going on with those graphs by looking at contours. Right? Now, the best example I have of what these contours would look like, the way I picture it here, here in 3D, is to think about the temperature function. So I'm standing here in my home office making this video, and the temperature is different in different parts of the room. Right? My computer is a little warmer than the area around it. There's a light up up over there. There's a light lighting this place. I can't touch that light because it's too hot, right? It's well over 100 degrees. Sorry to anyone who's not from the United States and actually, the whole rest of the world uses Celsius. I can think in Celsius, but I don't. Anyway, 100 degrees is pretty hot. And it's February when I'm making this. The northeast wind is blowing. It's freezing outside. If I touch the windows, it's cold. So there's a temperature variation within this room from, let's say, 50 degrees at the window to 120 degrees at the light bulb. Around me, I'm a little bit of a heater. I'm 98.6 internal and giving off heat. And so every point in the room has a temperature, right? So the function I'm thinking about is temperature of XYZ. So you give me a location in the room and I can measure the temperature. Okay? Now the graph of that would have to move off in some other direction. XYZ, I'll use W, I guess. So W will be a function of the temperature at each point. Now, what does that graph look like? I don't know. But what I can do is I can look at contours. I can say, pick particular values. Say, give me every point in the room where it's 100 degrees. And there'll be a little bubble around the light bulb where it's exactly 100 degrees. Inside that bubble will be hotter than 120, or hotter than 100 degrees, and outside the bubble will be cooler than 120 degrees. I could say, give me all the places where it's 65 degrees, right? And there'll be these areas around each of the windows where it's exactly 65 degrees. You could pick any particular temperature and say, give me all the spots in the room where it's exactly that temperature. And you'll have some weird shape, right? Those shapes are not curves, they're surfaces. There'll be a whole surface of points. And so rather than calling them level curves, I call them level surfaces. Right? So a function of two variables has level curves in the plane. A function of three variables has level surfaces in space. Okay? I still call them contours. Maybe I'd call them a contour surface as opposed to a contour curve. But I still think of them as contours. That is, places where the function value is constant. So that's really the way I picture a real function of three variables, right? That temperature is a real function of three variables. And we can look at the contours to get some idea what's happening with the graph. Now, I also want to just give you some examples here of some functions, some simple ones, some not so simple ones. It's because they're awesome. Here's a really basic one, just linear. W is a function of X, Y, and Z. So when I'm talking about contours or level surfaces, I'm saying pick a value of w and see what it has for a graph. So for instance, if w equals 0, I'm looking at 0 equals x plus y plus z. This is a plane through the origin with normal vector 1, 1, 1. So I believe in this picture down here, that's the green plane. And then you could say, okay, how about x plus y plus z equals 1? And, well, it still has the same normal vector, but now it goes through a different point. It goes through the point 1, 0, 0, or 0, 1, 0, or 0, 0, 1, right? So that would be maybe this red plane here. And then you say, okay, now I want x plus y plus z equals 2. And that would be a similar plane. I mean, it would be parallel to the other ones because it's the same normal vector, but it goes through different points, right? So that would maybe be this purple plane. Or you could say, give me minus 1 for the blue plane, or minus 2 for the orange plane down here, right? Let me pull up. So this is going to allow us to view it, right? These are all parallel planes. There's a bit of perspective in the drawing here, so the faraway stuff looks closer together. So this would be level surfaces for the function w equals x plus y plus z. They're all parallel planes. Okay. Now let's try something a little more complicated. How about w equals x squared plus y squared plus z squared? This is like a hyperparaboloid, right? If it was just w equals x squared, in the plane, you would have a parabola. If you had w equals x squared plus y squared in space, you've got a paraboloid, right? You take a parabola and spin it around its axis of symmetry. W equals x squared plus y squared plus z squared. Well, now you've got a paraboloid that's being spun around its axis of symmetry, but don't spin in xyz space. You got to spin in 4 dimensions to create this thing, and that's a little trickier, to visualize. But the thing is, I can look at cross sections. If I have a paraboloid in space, right? Just z equals x squared plus y squared. The level curves we saw in the previous video were circles, right? That is, when you cut that paraboloid with z equals a constant, you've got a circle. And depending on how high or low you cut, you've got either bigger circles or smaller circles, right? Well, here what happens, if you slice it at w equals 0, then you've got 0 equals x squared plus y squared plus z squared. That's just a single point. But if you slice it at w equals 1, then you'd get 1 equals x squared plus y squared. That's a sphere of radius 1. Slice it at level 2. 2 equals x squared plus y squared. That's a sphere of radius radical 2. Slice it at 3. You'd have a sphere of radius radical 3. Slice it at 4. You'd have a sphere of radius radical 4, which is 2, right? So as you keep slicing higher and higher in the w direction, you get bigger and bigger spheres as cross sections. What we got to figure out how to do is how to stack those spheres up. The problem is we can't, when we look at a circle, we can see that the circle is flat in one direction, and we can see that's the way we stack them up to build our paraboloid, right? But what we can't see, because we live in 3D and we're looking at 3D objects, we don't see the direction where those spheres are flat. We don't see that fourth direction, which, because it's just a three-dimensional object, doesn't have any length in that fourth direction, so it's flat. And that's the direction that we'd have to stack these spheres up. So here's the static view of that. So I've got 1, 2, 3, 4. I told it to draw 5, so there must be a sphere inside that blue one that we're not seeing. But there's sort of the nested spheres, which are the contours of w equals x squared plus y squared plus z squared. If I look at that in a movable way, you can see that they're all nested together. And of course, I'm only drawing one little bit of space. They would continue bigger and bigger and bigger spheres. What's not clear to me here, because I'm not exactly sure what WAMAP is, not WAMAP, what is this, Mathematica is doing. But they should be getting closer together, right? That is, for equal step up in W, the radius of the sphere doesn't get proportionally bigger. It gets a little bit bigger and less and less. That is, this is getting steeper each time because you're moving. W is increasing parabolically, quadratically, with X, Y, and Z. Right? So you're getting steeper and steeper, and so those level curves, those level surfaces should be getting closer and closer together. Okay. I'm not sure what numbers Mathematica is choosing with its level curves there. I just said draw me 5. Okay. So anyway, there's that one. Now, how about if we, rather than doing plus, 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 what if we make one of these minus? So that's my next example. So here's W equals x squared plus y squared minus z squared. The thing is now, when you look at level surfaces, plug in W equals a constant. Pick a constant. Let's say 0. X squared plus y squared minus z squared equals 0 is a cone. And I believe it's that blue one in there. We'll move it around and look here in a moment. If you pick W equals 1, you got 1 equals x squared plus y squared minus z squared. Well, that's a hyperboloid of one sheet, like this green one. Or if x squared plus y squared minus z squared equals 2, then you got a bigger hyperboloid of one sheet, maybe the red one. X squared plus y squared plus z squared, sorry, x squared plus y squared minus z squared equals 3. You get an even bigger hyperboloid of one sheet. X squared plus y squared minus z squared equals negative 1 actually becomes a hyperboloid of 2 sheets, because if you multiply both sides by negative 1, then you'd have 1 equals minus x squared minus y squared plus z squared, and now you've got a hyperboloid of 2 sheets, like this yellow one. Let's take a look at that in motion. All right, let's move it around here. So yeah, you can see that blue one is definitely right down in the middle there. Blue one is a cone. The yellow one is a hyperboloid of 2 sheets, where the green, the red, and the purple are all hyperboloids of 1 sheet. Awesome. What does this actually look like in 4D? Not a clue. I really don't have a clue. But I get some sense of what that function is doing in different places. You know, give me the places where that function is equal to 0. Well, it's everywhere on the cone. Give me places where that function is equal to 1. Well, it's everywhere on that green hyperboloid. Right? Hyperboloid of 1 sheet, and so on. Another example. Yeah, this one, one of my favorite ones I said surfaces of, function of 2 variables was z equals sine x plus sine y was an egg carton. So let's go one step up. W equals sine x plus sine y plus sine z. So this is like a three-dimensional egg carton stuffed out into 4th dimensions. I mean, W varies like a sine curve with x, with a sine curve with y, and with a sine curve with z. And so then I plot the contours of this thing, and oh my goodness, this is why I do math. This is why I do math, so that I could draw these pictures. Oh man. Let's see that here. Oops. So here it is in motion. Someday I want to build a playground, play set, and just use the green, right? If you use the green is where W equals 0. So sine x plus sine y plus sine z equals 0 is the green surface. This function gets as high as 3. It gets as low as negative 3. And So I don't know, I didn't figure out which way it goes, but green is 0, and so then the blue is either +1 or -1, and then the orange is +2 or -2, and the purple is the other one, right? And so yeah, but that green, if you could get close in and see, it's one surface that just weaves its way through, and it cuts space into 2 separate regions, 2 identical regions that are like the tunnels, honeycomb tunnels all over the place. And so you could be crawling around inside, and someone else could be crawling around outside, but their outside would look the same as your inside, and you'd never meet each other because you'd be on opposite sides of this crawling play space. This is just crazy. Someday I will build this contour, the green one. Of course, the red and the blue ones are kind of fun too, because they also are tunnels that go, that you can start in here and head through there and come out over this way or head in there, but they get really skinny. And the red one does the same thing on the other side. I just want to conclude by compare this picture here, this one, with the contour plot for the the function of 2 variables, just z equals sine x plus sine y. Right? You have the very straight parts of it where it was the contour for level 0. Likewise here, the green was the contour for level 0. And then with the positives here, you've got these sort of nested smaller and smaller. They're not really circles, they're kind of squarish circles, but they get very, very circular towards the top of the bulb here. And likewise here, these are kind of squarish ovoids. Right? But they get rounder as you get closer to the top of that bulb. And of course the negatives do the same thing, but in the other direction. Right? There's a really strong similarity between the shapes that we have there and the 2D thing, or 2D because it's contours of 3D, and here 3D because it's contours of 4D. I was about to conclude and say I'll put a link, but here, CalcPlot 3D can do these contours. It does them one at a time. Mathematica, I could draw a bunch of them at a time, but here's one at a time. So here's sine x plus sine y plus sine z equals a, and I have a being able to, I was hoping to animate it, but maybe I can. Let's try animating it. So this is running through different values of a. So these are positive values, so the contours are getting, you're slicing higher and higher on that egg carton, right? If you got a 4-dimensional chicken laying 4-dimensional eggs, this is what you would put them in. So there's right at the top, and now it's coming back down. So now I'm watching the slider over here. So I'm coming down, slicing lower and lower. Right. And now we get into the middle, right, where's the middle? Right there, right? And now we're getting down to the bottom part, and you can see all the different slices of that. This is CalcPlot 3D. I will put a link if you want to do a contour like this under the, let's pause this. So what you want to select is you want to select implicit surface. The implicit surface is, it's like an implicit function, right? That you just have an equation. You don't have it spelled out. Z is a function of x and y. You just have an equation with x, y, and z in it. So, for instance, the one I have here, I have sine x plus sine y plus sine z equals, I'm using a because I want to be able to use the slider here and just slide this thing around and see the different slices. All right. CalcPlot 3D. It's a pretty versatile online 3D graphic tool. Anyway, there you go. There's contours of functions of 3 variables trying to visualize what's happening with a graph in the 4th dimension. Enjoy.